settle in by the shore of thought, where the sky meets water. We'll drift together through a quiet harbour of stars, watching for the faintest wakes of distant worlds. You don't need formulas to feel the rhythm of discovery. Think of stars as lanterns along a dark quay, and planets as boats circling those lights. We can't usually see the boats directly, but we can read their ripples, silhouettes and tugs. That's the heart of exoplanet hunting, watching careful changes in starlight, like a patient harbour master noting every small sign. The harbour is crowded with lanterns, each one a sun warming its own patch of night. From our pier, the Milky Way looks like a street of lamps receding into mist, but almost every lamp has company. Boats circling, mooring, slipping behind pilings and reappearing. In everyday life, we learn our shoreline by noticing patterns, tide marks on posts, gulls taking flight, the way the water flattens near a hull. Astronomers use the same instinct. We stare at the lanterns and let small repeating signs teach us the shape of what we can't see. When you picture the night sky, it's easy to imagine it's sparse, but surveys show the opposite. Planets seem common, as routine as dinghies beside fishing boats. Our own solar system is just one marina. There are unimaginably many. The delight isn't only in the numbers, though, it's in the subtlety of the methods. Like spotting a moored boat by the way the tide swirls around it, we watch light for clues. Dips, shivers and colours, each hinting at size, rhythm or temperament. The simplest sign is a soft dimming. If a boat crosses a lamp, the light dips for a heartbeat. If that repeat happens at regular intervals, we infer an orbit. Another sign is a tug on the lamppost. A heavy boat makes the post wobble, however slightly. Translate that to space, and a star's tiny sway betrays a planet's pull. Over years, these techniques have turned the sky from scenery into a charted harbour, with lanes, clusters, and traffic we can sketch in rough but faithful lines. It helps to ground this in plain physics. A star and its planet orbit their shared centre of mass, like dancers leaning against each other. The star is massive, so it moves only a little, yet that little is measurable. Light dims when a planet passes in front, this is a transit, and brightens again when it's gone. We call the brightness record a light curve, a simple graph of lantern glow versus day. From its shape we learn size and path, the way a dockhand learns a boat by its wake and rhythm. The wonder here is humility. We're not capturing postcards of other Earths, we're reading shadows and sways. It's less like sightseeing, more like listening to an old pier creak and knowing the weather is changing. Speculative. Some lanterns may host worlds with oceans and breezes not unlike our own. But we speak carefully because signs can mislead. Dust can dim. Spots on a star can be mistaken for a passing hull. That's why the harbour master keeps a log, checks again, and compares notes. This turns the night into a shared craft. Instruments become our eyes, but patience remains our muscle. When we watch a steady light falter by a fraction, we're doing what mariners have always done, attending to the small stuff. The reward is insight without spectacle. We don't need fireworks. We need clean, repeated patterns and the calm to wait for them. The lanterns do the rest, beaming across the black water, greeting our quiet curiosity. If this brought you a little calm, feel free to like and subscribe, and tell us where you're listening from and what time it is there. As the harbour fills with mapped routes, we begin to see families of worlds. Some boats hug the lamppost, racing in tight circles. Others roam wide, returning after long arcs. Some are hulking barges, the hot Jupiters, towing their wakes close to the light. Others are neat mid-sized craft that our own marina lacks. Even when we can't glimpse the hulls, we can sketch them from their effect on the glow and the pole. That is the quiet triumph of exoplanet discovery, finding a living harbour in the dark, one sign at a time. At first, hints are all we have, the sort you get from the corner of your eye. A lantern's glow softens for a beat, then steadies. The pole holding it seems to shift by a hair. In a busy harbour, you don't declare a boat from one ripple. You watch for repetition. Is the dip regular, like the sweep of oars? Is the sway consistent, as if a tug passes the post every so often? Those are the early twitches of new worlds, wobbles and dimming, modest clues that become compelling when they line up. The dimming is the more intuitive hint. Picture a skiff sliding between you and a pier lamp. For a moment the lantern peeks around it, and the total glow you perceive drops a little. In astronomical terms, when a planet crosses the face of its star, we see the starlight dip. The amount tells us the planet's size relative to the star. A bigger hull covers more light, making a deeper notch. The duration tells us about speed and path. A longer crossing usually means a slower or longer route across the face. The wobble is subtler. Imagine a barge tugging gently on the lamppost with a mooring line. The pole leans a fraction, then relaxes, then leans the other way, in a rhythm shared with the barge's orbit. Stars do this. They don't sit still while planets circle, they move in tiny loops around a shared balance point. The star's motion toward and away from us nudges the colour of its light by a smidge, bluer as it comes, redder as it goes, like the way a siren changes pitch as an ambulance passes, only with light rather than sound. When both hints appear together, dimming at regular intervals and a matching wobble, we gain confidence. The dimming alone could be a patch of dark cloud, a star spot, or instrumental mischief. The wobble alone could be caused by star surface jitters or blended light from a neighbour, but the two combined form a sturdy pair: silhouette and tug, shadow and sway. The harbour master marks them, watches for a pattern, and tests the gear. In practice, astronomers run careful checks, correcting for the star's own tantrums and the instrument's quirks. These first hints brought the field to life. In 1995, the wobble of a sun-like star revealed a hot, hefty companion in a shocking close orbit, like a trawler circling a lamp at arm's length. Later transits turned trickles into floods, as space telescopes stared at thousands of lanterns at once hunting for dips. The two methods complement each other. Dimming tends to find planets with orbits that line up edge-on, while wobbles can work at more angles but favour massive or close-in worlds. Together, they make the harbour feel real, not imagined. The metaphor holds when we consider false leads. A gull flying across a lamp could mimic a boat's shadow from afar. A loosened bracket might make the pole sway without any tug from the water. That's why we cross-check. We look for the same period in both hints. We compare colours and examine neighbouring lights. We schedule follow-up observations to see if the pattern holds. Speculative. Occasionally, a pattern that looks like a planet may be a grazing binary star, two lanterns eclipsing each other so shallowly they masquerade as a hull. Caution keeps the chart clean. We should also celebrate how humble equipment can be souped up for truth. A ground-based telescope like Eyes on the Key deals with shimmering air. Space telescopes avoid that shimmer but have their own wrinkles, thermal shifts, detector quirks. In both cases, we learn to subtract the gusts, leaving the tide. Early hints are fragile, yet persistence turns them into discoveries. That first quiver in the pole, that first dimming of the light. When they repeat with the grace of orbits, we add a dot to the map and quietly update our sense of what's out there. A light curve is a diary of a lantern's glow, dot by dot across nights, captured with care. Like watching the brightness of a pier lamp from your window, you mark when it seems a touch lower, when it returns to its usual shine, and whether the pattern repeats. When a planet transits, slips across the star, we get a characteristic dip in the curve. It's a clean, geometric signature, like a neat notch on a tide chart. Read it well, and it reveals size, orbit, even hints about the atmosphere hugging the hull. Start with depth. If the lamp dims by 1%, the planet's disk covers 1% of the star's face. That gives a size ratio. Knowing the star's actual size, which we estimate from its colour and brightness, lets us assign a physical radius to the planet. A deeper dip means a larger world. The duration matters too. A longer dip with the same period often points to a wider path across the face, or a slower orbit. The shape of the dip's edges, the way brightness falls and rises, tells us about the star's limb darkening, the natural fade toward its edges. Sometimes the dip isn't a perfect U-shape, it's V-shaped, suggesting the planet grazed the edge of the star. That makes size estimates trickier. Occasionally, we see slight brightening just before and after the dip, a sign of starlight scattering around the planet. Speculative and subtle, but suggestive of atmospheric hazes. A sequence of dips, each the same depth and spacing, builds a case for a planet. Variations in timing can hint at other worlds tugging the transiting one, shifting the schedule. Even small quirks become tools when treated with patience. Noise is the sea's chop. The harbour water never sits perfectly still, and our measurements don't either. Clouds drift through, the air wobbles, the instrument warms and cools. We counter this by taking many measurements and letting the truth emerge statistically. The repeated pattern of transit stands out against random gusts. We also compare nearby lanterns, reference stars, to correct shared hiccups. The aim is to isolate the planet's signature, a repeating modest notch that persists when the rest of the scene is accounted for. Once we have a reliable light curve, we can model the geometry. An orbit that's edge-on gives a central, deeper dip. A tilted track gives a shallower, longer graze. The period between dips reveals the orbital length. Combined with the star's mass, this tells us how far the planet sits, like measuring the radius of a boat's circle around the lamppost. Knowing that distance is key for temperature estimates and for context. Is this a hot inner lane, a temperate middle run, or a cold outer circuit? Sometimes we can detect a tiny secondary dip when the planet slips behind the star. That's not a transit, but an eclipse of the planet's own light. It can tell us about heat and reflectivity, how shiny the hull is, and about the planet's dayside temperature. Even if the secondary dip is too small to see, phase curves, gentle, cyclical brightenings and dimmings as the planet shows us different faces, can whisper about weather and clouds. All of this comes from a single stream of brightness measurements, treated like a careful tide log. Light curves taught us to see planets in crowds. Space missions dedicated to staring at stars turned light curve analysis into a factory of new worlds. Yet the craft remains personal. Each curve is a story, and each story demands skepticism and care. We cross-check with other methods to confirm and refine. That way, the notch in the light becomes not just a hint, but a measured world with a radius, a period, and a place in the harbour map. From simple dips, we draw real boats, one curve at a time. If transits are the silhouettes, radial velocity is the hand on the post. Picture placing your palm on the lamp's pole and feeling it lean, then lean back as a hidden boat tugs its line. That back and forth becomes a rhythm you can chart. In space, we can't touch the pole, but we can read the star's motion toward and away from us in its light. It's like detecting the slight pitch change in a whistle as it moves. Only here, the colour slides by a hair and sensitive instruments catch the shift. This method centres on the Doppler effect. When a star comes towards us, its light waves bunch up slightly, nudging them toward blue. When it moves away, they stretch a little, nudging toward red. We measure this by splitting starlight into a spectrum, the rainbow spread into thin lines, and tracking those lines' positions over many observations. A periodic wobble in those lines means the star is orbiting a shared centre with something unseen. The amplitude of that wobble tells us the strength of the tug, tied to the companion's mass and the orbit's tilt. A heavier planet gives a bigger tug, like a stout tugboat compared to a dinghy. A closer orbit too increases the pull, but there's a catch. We feel only the component along our line of sight. If the orbit is not edge-on, we see a smaller sway than the true one, so radial velocity gives us a minimum mass. Pair it with a transit, which tells us the tilt, and we can pin down the actual mass. That combination is powerful, turning a wobble and a dip into a weighed, measured world. The instruments that do this are astonishingly steady. They lock onto spectral lines like a helmsman keeps a compass steady and swell. Even so, stars have moods. Their surfaces boil, spots appear and vanish, and magnetic cycles shift the lines. We learn to separate those from orbital tugs by looking at different indicators in the spectrum, by tracking the line shapes as well as their positions, and by gathering enough data that transient flutters average away. The goal is to recognize the smooth, repeatable rhythm of a real orbit. Radial velocity found the first hot Jupiters, giants whipping close to their stars. Those tugs were big and frequent, hard to miss. As instruments improved, we began to feel the feeble pulls of smaller, wider worlds, edging toward the realm of super-Earths and even Earth-mass planets around quiet stars. Speculative. The lightest tugs we now claim live near the threshold where stellar noise may masquerade as planets, so debate keeps us honest. Healthy skepticism is part of the craft. We prefer strong, repeated signals and independent checks. Think again of the harbour. You can't see the boat in the fog, but your hand on the pole tells you it's there. You sense its mass and rhythm. Paired with the faint shadow you recorded earlier, you now know its size and weight. From that, you can guess its build, rocky like a skiff, puffy like a raft, or hulking like a barge. Radial velocity is the tactile partner to transit's visual whisper. Together, They turn distant lanterns into sources of full practical knowledge. The delight is also in what we can infer about orbits. A circular loop produces clean, sinusoidal sways. An elongated path gives asymmetric tugs, faster at closest approach and slower at farthest reach. That shape hints at histories, gravitational nudges, past upheavals, migrations inward or outward like boats changing berths. With enough systems measured, we see trends across the harbour, learning not just single boats, but the port's culture. Some lanes crowded with heavy close-in craft, others filled with balanced flotillas more like our own. Shadows and silhouettes carry different stories depending on who hides whom. Imagine two lanterns and a boat circling one of them. When the boat passes in front of its lamp from our point of view, we see a transit. The lantern's glow drops because an object blocks part of it. That's a silhouette. When the boat slips behind the lantern, the planet's own reflected or emitted light vanishes for a moment. That's a secondary eclipse. Both are useful, like watching a boat stride past a lamp, then disappear into the glare behind it. Transits primarily tell us the planet's size because the amount of blocked light relates to the area of the planet's disk. Secondary eclipses tell us how bright the planet is on its day side. If the planet glows warmly in infrared, heat it has absorbed and re-radiated, the disappearance of that glow when it goes behind the star causes a tiny drop in total light. Measuring that drop lets us estimate the dayside temperature and reflectivity. A shinier, cloudier planet reflects more starlight. A darker, clearer atmosphere absorbs and re-emits more heat. The timing of these events also matters. If the secondary eclipse happens exactly halfway between transits, the orbit is likely circular. If it's offset, the orbit is elongated. The depth of the secondary eclipse depends on wavelength. Look in different colours, and you sample different layers of the planet's atmosphere. That's like peering at a boat with different lantern colours to see the difference between polished deck and darker hull. A spectrum across the eclipse can reveal molecules, water vapour, carbon monoxide, even hints of clouds or hazes in the way brightness changes. Eclipses shouldn't be confused with star-on-star eclipses, which can mimic planetary transits. Two lanterns eclipsing each other can produce shallow dips if one is faint. Careful vetting distinguishes them by the depth ratios in different colours, by the shape of the dips, and by signs of two stellar spectra. The principle is the same harbour wisdom. Know whether the shadow belongs to a boat or another lamp. Instruments built for precision, plus cross-checks from radial velocity keep the chart honest. Silhouettes can flash nuance. A grazing transit where the planet clips the star's edge yields a V-shaped dip, less informative for size but still useful for timing. Multiple transiting planets can cause blended dips, like overlapping wakes. Careful modelling separates them. Speculative. We sometimes see hints of exomoons in transit shapes, or rings around a giant world causing subtle shoulders on the light curve. These remain tentative because the data are delicate, but the silhouette method keeps teasing us with the possibility. Secondary eclipses open a window to weather. If the planet's hottest spot is shifted east or west of the substellar point, the spot facing the star, you'll see the peak of the phase curve move before or after the secondary eclipse. That's like noticing steam rising from a galley not directly under the lamp but offset by winds. It suggests strong jet streams transporting heat. Clouds complicate the picture. They can brighten the reflecting side while masking the true thermal glow. By fitting models to multicolour measurements, we pull apart these contributions. Transits and eclipses together turn starlight into stories of surfaces and skies. They benefit from patience and repetition, especially for small planets whose dips are shallow. Instruments in space do best, freed from atmospheric flicker. Ground observers add agility and follow-up. The technique's power lies in its geometry. Alignments are rare, but when given, they gift us an exceptionally direct way to weigh, measure, and even take a weather report from a world we can't see. A harbour of lanterns becomes a world-by-world diary, written in silhouettes and light. Noise in a harbour sounds like gulls slap and wind through rigging. It's always there. If you want to hear a single oar dipping, you learn to filter the clutter. In exoplanet work, the same discipline applies. Stars are restless, instruments wander, the air shimmers. Our job is to tease out the tiny repeating signals, the oar strokes from the racket. Start with the star. Its surface boils with convection, creating granulation that flickers brightness. spots and flares come and go, imprinting periodic modulations as the star rotates. These can mimic or mask transit signals. We mitigate them by observing over timescales longer than the star's rotation, by modelling the star's activity with separate indicators, and by using multiple wavelengths. Star spots usually darken more in some colours, while a planet's silhouette darkens all wavelengths equally. We also treat flares and outliers as transient gusts, excising them or down-weighting their influence. Instruments add their own chatter. Detectors warm and cool, slightly changing sensitivity. The telescopes pointing drifts, moving starlight across pixels with uneven response. We correct this with calibration frames, flat fields, and by tracking the centroid of starlight to decorrelate brightness with position. Space telescopes have their characteristic quirks that become familiar with time. We build noise models, not just for randomness but for correlated noise. The slow sway of the pier, not just the quick splashes. The atmosphere on Earth is a storyteller too, though sometimes an unreliable one. Turbulence blurs images, water vapour absorbs wavelengths, and clouds simply get in the way. We work around this by choosing dry sites, using adaptive optics to sharpen images, and by building networks of observers to cross-check and fill gaps. Differential photometry, comparing our target star's brightness to nearby reference stars, helps cancel shared variations. Think of it as listening to several lamps at once. If they all flicker in sync, blame the air, not a passing hull. Statistics become our ear training. We fold the light curve on trial periods, stacking observed cycles, to see if a dip builds coherently. We use periodograms to hunt for significant frequencies. We test our models with injection recovery experiments, adding fake transits to real data to check detection sensitivity. This bridges optimism and reality. Knowing what we can't detect is as important as celebrating what we can. It keeps our catalogue honest, defining the harbour's blind spots. Sometimes the data resist tidy interpretation. A quasi-periodic signal could be a planet with a variable transit depth, maybe clouds, or a star's evolving spot pattern. We look for corroboration from radial velocity, high-resolution imaging to rule out blended stars and colour-dependent signatures. Speculative. Machine learning aids are appearing, promising to flag planet-like dips efficiently, though we treat them as assistants, not oracles, because pattern recognition can be fooled by novel noise. Cleaning doesn't mean scrubbing away the truth. It means respecting the physics of both the signal and the noise. We avoid overfitting, forcing the data to match our hopes, by holding back some data for validation, and by testing simpler models. We publish uncertainties, honest bands of doubt, because the sea will always have a little chop. That humility is not a burden, it's a strength, a way of keeping our chart useful for everyone else sailing these waters. As a craft, data cleaning rewards patience. Think of it as mending nets by lamplight. Each knot matters. When done, the catch holds. A transit depth we trust, a wobble we believe, a phase curve that reads like weather. Then the little oar strokes stand proud against the gusts, and a world we can't see becomes measurable. The harbour quiets, not by silencing nature, but by learning its rhythms well enough to hear something new. Imagine weighing and measuring a boat from its ripples and the pole it tugs. From the transit depth, we get size, the planet's radius. From the radial velocity wobble, we get mass. How much tug on the star? Put them together and we get density, mass divided by volume, which hints at composition. A dense world is likely rocky, a lighter one puffy with gas or ice. It's like deciding whether a silhouette belongs to a skiff, a pontoon, or a barge. Radius comes first, mathematically simple even if the measurements are delicate. If a star is well characterized, its radius and temperature known, we can turn a 1% dip into a precise planetary size. Star uncertainties still bleed into the answer, so better star data mean better planet data. Mass from radial velocity has its own caveats, tied to orbital tilt. A transiting planet gives us that tilt, allowing a true mass. For non-transiting worlds, we speak of minimum mass, a cautious lower bound. Density is storytelling material. Worlds around Earth size with Earth-like density probably have iron cores and rocky mantles. Larger planets with similar densities could be water-rich, with deep oceans or high-pressure ices. Low-density giants, especially close to their stars, can be bloated by heat, their atmospheres puffed up like warm balloons. We also compare density with incident starlight, how much energy the planet receives, and with age because planets evolve. Young giants shrink, old ones settle. Speculative. Some planets may hide massive cores beneath thick hydrogen envelopes, blurring simple categories. The mass radius diagram becomes our harbour's registry. Each dot is a boat with measured size and weight. Clusters reveal families, rocky super-Earths, volatile rich mini-Neptunes, and gas giants spanning a range of inflation states. Gaps too appear. One famous feature is the radius valley, a dip in the number of planets between about 1.5 and 2 Earth radii around certain stars. It likely reflects atmospheric loss, where some mid-sized worlds had their gas stripped, leaving compact rocky cores, while slightly larger ones kept their envelopes. Density also informs atmosphere expectations. A puffy world with low gravity holds a generous atmosphere that's easier to probe with transmission spectroscopy. A dense, compact world has thinner air, harder to sample. But density is a bulk clue, not a full answer. Different mixes, iron, rock, water, gas, can conspire to give similar averages. We broaden the picture with other data: thermal measurements, phase curves, and the presence of siblings, which hint at formation pathways. Errors and uncertainties deserve gentleness. A small bias in stellar radius skews every planet's size and density. Community efforts to refine stellar properties, using astroseismology and Gaia astrometry, have sharpened our planet catalogues. Revisions happen. A world once hailed as Earth-like might shift to sub-Neptune territory after better star data. That's not failure, it's harbour maintenance, repainting lines to match the true positions of posts and buoys. Measuring size, mass and density turns whispers into individuals. From those numbers, we infer gravity at the cloud tops, surface conditions and escape speeds. That, in turn, feeds our sense of habitability and exploration priority. We're not just collecting trophies, we're learning which boats might carry rocky shores, which carry storm-tossed skies, and which are warm balloons where a sunset lasts forever. With every weighed and measured dot, the harbour gains character, and our own dock feels less singular. Every harbour has a mild lane where a boat's paint lasts longer, and the crew keeps a comfortable watch. In planetary terms, that lane is the habitable zone, the range of distances from a star where a rocky world could host liquid water on its surface, given a plausible atmosphere. It's a simple idea with elastic edges, like a band on a map rather than a painted line on the pier. The star's brightness sets the broad scale, the planet's air and clouds fine-tune the experience. For a sun-like star, this band wraps around where Earth sits. For cooler, dimmer stars, the band nestles closer in. For hotter, brighter stars, it lies farther out. But distance isn't destiny. A world swaddled in thick greenhouse gases could be warm enough even beyond the classic band, while a world with sparse air might freeze inside it. Cloud cover can reflect light and cool a planet, or trap heat and warm it. Habitable zone therefore means temperate possibilities, not guaranteed beaches. We talk about the inner and outer edges. Move too close and water boils away in a runaway greenhouse. Drift too far and water freezes, perhaps only thawing under special circumstances like strong greenhouse blankets. The exact edges depend on assumptions: what gases, what surface, what cloud physics. Speculative. Exotic atmospheres could widen or narrow the band in ways our Earth-trained intuition doesn't expect. Even so, the idea is useful. It focuses searches and frames conversations. Around small, cool red dwarfs, the habitable zone is tight and nearby. That makes transits frequent and deep, so these systems are easier to study. But such stars can be active, flaring and bathing close-in planets in radiation. Tidal locking is likely, where one side always faces the star, creating a permanent day and night. That's not disqualifying. With a thick atmosphere or ocean, heat can circulate, making the twilight belt temperate. The harbour metaphor helps here. A snug berth near a busy jetty comes with its own challenges and conveniences. We also think beyond surfaces. Subsurface oceans under ice shells, warmed by tides, could exist far outside the classic habitable zone. They're like cosy cabins below deck, shielded from the weather. These worlds may be common, though harder to study from starlight alone. The simple habitable zone ring doesn't capture such possibilities, but it remains a helpful first filter for where to look for Earth-like conditions we understand well. Finding a planet in the habitable zone isn't finding a twin. We still need to know size, mass, atmosphere, and stellar temperament. Clouds may hide signs. Photochemistry can confuse. Yet the band gives a starting point. When we see a rocky radius planet orbiting within that ring, our attention sharpens. We plan spectroscopy to sniff for air, and we model climates under different assumptions. It's a long, careful game, but the promise is clear. A temperate lane, calm enough for liquid water, is worth charting with special care. In the end, the habitable zone is an invitation, not a guarantee. It keeps us honest about what matters for life as we know it: energy balance, liquid water, and stable air, while welcoming surprises. The harbour has many lanes. Some will be balmy, others blustery. By naming the calmest stretches, we organise our lookout and give our curiosity a sensible place to rest between discoveries. Between Earth and Neptune sits a broad missing berth in our marina. We have no native mid-sized planet, but other harbours brim with them. Astronomers call them super-Earths and mini-Neptunes, worlds larger than Earth but smaller than Neptune. Some are likely beefy rocks with thin atmospheres, others are cores wrapped in puffy gas or steam. They blur old categories. In the silhouetted catalogue, they dominate, proving that nature likes this size, even if our local peer doesn't. From transits we get their radii, from wobbles their masses, densities scatter. A 1.5 to 2 Earth radius world can be rocky or volatile rich depending on mass. Around 1.6 Earth radii, statistics show that radius valley, hinting at atmospheric loss sculpting the population. Close to the star, intense light can strip lighter atmospheres, leaving compact, denser worlds, super-Earths. Slightly larger or farther out atmospheres survive, mini-Neptunes. It's like seeing two families of boats at neighbouring berths, sturdy skiffs and softly inflated pontoons, shaped by exposure to spray and sun. Super-Earths are tempting. Heftier than Earth, they might retain thick atmospheres and vigorous geology, with strong gravity anchoring mountains and oceans. Plate tectonics could be robust or stifled. We don't know. Speculative. Some might be water worlds, with deep global oceans over high-pressure ices, lacking continents. Surface life there would be strange if present, relying on nutrient cycles without land. Mini-Neptunes intrigue for different reasons. Their thick hydrogen-rich envelopes may host high clouds, hazes, and layered weather, with temperatures ranging from pleasant to fierce. These worlds are prime targets for transmission spectroscopy. Their puffier atmospheres, if clear, imprint stronger, more detectable features in starlight. We've begun to see water vapour, hazes, and hints of carbon-bearing gases. Clouds often veil the scene, flattening expected signals like a tarp over a deck hiding the gear below. That too is a finding, teaching us about aerosol formation, temperature, and metallicity. The abundance of elements heavier than helium. We learn which boats sail with bright varnish and which carry matte, weathered finishes. Formation stories add flavour. Did mini-Neptunes form beyond the frost line, where ices are plentiful, and migrate inward, carrying volatiles with them? Did super-Earths form in place from metal-rich disk material, building dense cores quickly? The distribution of their orbits, the chemistry of their stars, and the presence of siblings help us choose between tales. Many systems show chains of similar-sized planets, evenly spaced, like tidy moorings. Others are mixed, hinting at past jostling. The harbour remembers its drama in the arrangement of its boats. Our missing local example sharpens our curiosity. Without a native super-Earth or mini-Neptune, we lean on models and on distant measurements. That's fine. The variety we see elsewhere broadens our sense of possible worlds. It suggests that habitability might take forms we haven't pictured, and that planet formation doesn't follow a single script. In the gentle glow of other lanterns, mid-sized worlds glide by, numerous and patient, inviting us to keep refining our eyes, ears, and charts for the busiest berths in the galactic harbour. Hot Jupiters are the harbour's showstoppers, hulking barges spinning absurdly close to their lanterns, hissing with heat. They orbit in days, not months, and their sizes make their shadows unmissable. Their existence surprised everyone. Our own giant sits far from our sun, a steady anchor in the outer lanes. Finding giants tucked against their stars was like discovering a freighter moored right under a street lamp, circling the post in dizzy loops. Why are they there? The likely answer is migration. Giant planets form where gas and ice are abundant, far from the star, then move inward by interacting with the disk or with other planets. Disk migration is smooth, like drifting inward on a tide. Planet-planet scattering is rowdier, with close passes and changed tilts. We read the history in the present, orbits that are aligned, circular, and close hint at gentle inward drift. Orbits that are tilted or even backward suggest past upheavals, later tamed by tides. Their proximity makes them fantastic laboratories. Daysides bake to thousands of degrees. Nightsides may be cooler but still scorching. Strong winds transport heat, shifting hotspots and sculpting phase curves. Transmission and eclipse spectra reveal atmospheric chemistry. Water vapor is common. Sodium and potassium leave fingerprints, and carbon-bearing molecules appear depending on temperature. Some hot Jupiters are ultra-hot, hot enough to split molecules and ionize metals, creating exotic weathers, iron rain, titanium oxide haze. These are not quiet beaches, they're roaring engine rooms. We also see puffiness. Many hot Jupiters are larger than expected for their mass. The extra heat from the star, plus mysterious interior heating mechanisms, can inflate them. Several ideas compete. Energy dissipation by winds, ohmic heating from ionized winds moving through magnetic fields, or tidal energy. Speculative, different worlds likely mix mechanisms. Observations across temperatures and host star types help discriminate. The harbour metaphor helps again. Some barges swell with cargo and heat, their sides ballooned, riding higher in the water than a cold, compact twin would. Hot Jupiters may shape their systems. Their inward march can perturb or eject smaller neighbours, clearing inner lanes. That may explain why many systems with a hot Jupiter lack close small planets, while compact multi-super-Earth systems often don't host a giant. Even so, exceptions exist, keeping theories nimble. We're learning that planet formation plays many tunes, with migration as a common refrain, but with local improvisations. Detection bias played a role in their early fame. Big, close-in planets are easier to find, so they dominated early discoveries. As methods improved, the harbour filled with more modest craft. Hot Jupiters still punch above their weight in what they teach us, though, because their signals are strong. They anchor many of our techniques, providing testbeds for theories of winds, chemistry, and the interplay between star and planet. Their very oddness keeps us honest about our assumptions. At first glance, they seem too extreme to matter for habitability, but they teach the physics that underpins all atmospheres. They show how irradiation shapes circulation, how clouds form under stress, and how metals condense and fall. That knowledge translates to milder worlds. In the glow of these close-in giants, the practice of reading light becomes a more subtle craft. The big barges near the lamp may be noisy neighbours, but they've widened our understanding of how the whole harbour breathes, warms and weathers. When a planet steps across its sun, it's like an actor slipping between us and a stage lamp while wearing a gauzy scarf. Some of the lamp's glow passes through that scarf, colouring the light with tiny tints that betray the weave. A planetary atmosphere is that scarf. As starlight skims the planet's rim, the thin ring astronomers call the limb, it crosses layers of air before reaching our telescopes. Molecules in those layers nibble on certain colours. The pattern of nibbles is the spectrum, and each molecule prefers its own snack. Water vapour favours reds in the infrared. Sodium leaves a bold notch in the yellow. Methane, carbon dioxide, and carbon monoxide each paint their own shy fingerprints. By sorting the light and watching how deep a transit looks at different colours, we can read the scarf's pattern and learn what the air is made of. This trick is called transmission spectroscopy. Spectroscopy just means measuring how brighter or dimmer the light is at each colour. We use it because atmospheres are otherwise invisible. The planet itself is too small and too close to its blazing sun for us to see separately, but the silhouette grows a whisker thicker if the air is opaque at a given colour. That change is minute, often just parts per 10,000, but steady patience and repeated passes add up. Taller atmospheres make bigger signals. Scale height is the fancy phrase for how puffy an atmosphere is. Hotter gas, lighter molecules, and lower gravity all inflate the scarf, letting more starlight weave through and be marked. Of course, scarves can be plain. Clouds and hazes act like a blanket rather than a lace. Tiny particles high above the main weather can scatter light in a way that smooths the spectrum, turning crisp lines into a muted wash. We then speak of a flat spectrum. The planet seems to hide its chemistry behind a pale veil. Even a thin haze can smother subtle features, especially at shorter wavelengths where blue light bounces more easily off small grains. We can still learn from a flat spectrum, its slope, its slight colour trends, but it's like reading a whisper through fabric. The instruments doing this work are painstakingly tuned cameras with prisms and gratings. From space, Hubble opened the door, finding sodium around a hot Jupiter and water vapour in several puffy worlds. Now the James Webb Space Telescope listens across a richer range of colours, from orange-red to deep infrared. Each pass of a planet gives a new line in the script. On the ground, giant mirrors with steadying optics, systems that cancel the stars' twinkling, can add their own lines, though Earth's air draws scribbles we must subtract. Telluric features are our planet's imprints. Software peels them back like a reflection in glass. Extracting an atmosphere's recipe means solving an inverse puzzle. We start from the spectrum and work backwards to probable skies. That involves retrieval methods, careful statistical fits that weigh different molecules, temperatures, clouds, and particle sizes. There are degeneracies, where different combinations mimic one another. Is that dip from water, or from water plus high clouds? Is the muted slope due to haze grains or to heavier compact air? We chip at uncertainty by measuring more colours, by pairing data from multiple instruments, and by catching the same planet on different nights. Spectral lines have shapes that shift with temperature, pressure and wind, so every extra nibble of detail helps. Stars introduce mischief. The stage lamp isn't perfectly still. Dark spots and bright faculae on the star's surface can make transit depths look a little deeper or shallower, depending on which patches the planet covers. This stellar contamination can mimic atmospheric marks, especially if the star is active. We watch the star when the planet is elsewhere to map its moods, and we build models that account for spotted, mottled light. The goal is to separate the actor's scarf from the lamp's flicker. What can we learn when everything clicks? We can identify molecules and estimate their amounts in broad strokes. We can gauge temperatures at the limb, decide whether the air is clear or hazy, and guess at atmospheric metallicity, the abundance of elements heavier than helium, a clue to a planet's birth pantry. On hot Jupiters, we've seen sodium, potassium, water vapour, carbon monoxide, and hints of more complex chemistry. On smaller worlds, signals are thinner, but Webb has begun to pry open super-Earth and mini-Neptune skies, where hydrogen-rich envelopes or heavier, steamier mixtures leave different patterns. Speculative. A few of these small worlds may host water-dominated air with high-altitude haze born from star-like cracking molecules. Transmission spectroscopy is rarely a one-shot reveal. It's more like watching several matinees and evening shows, noticing when the scarf glints differently and when the air seems puffier after a flare from the star. Pairing these measurements with other approaches like eclipse depths or phase curves rounds out the story. Together they let us infer whether a planet's dayside bakes or breathes out heat, whether winds shear around like a jet stream, and whether the air holds onto lightweight gases or is boiled away. Each spectrum is a small confession, a soft aside from an actor passing the footlights, and taken together, they whisper the weather and chemistry of faraway stages. Think of a stage where the actors sometimes wear feathered capes and sometimes slick raincoats, changing outfits between scenes. Planetary atmospheres do that too in their own way. High clouds, hazes and gusting winds are costumes and choreography, reshaping what we see whenever a world steps into the light. A cloud is simply a collection of tiny droplets or grains suspended in air. A haze is made of even finer particles, often born when high-energy light breaks apart simple molecules and they recombine into soot-like smog. On hot exoplanets, these condensates aren't water alone. They can be silicates, metals, or exotic salts, forming at temperatures that would melt a saucepan. When we read a planet's atmosphere as a silhouette, clouds can blur the edges. In transmission, high veiling decks act like frosted glass flattening the spectrum. A gentle slope toward the blue can signal Rayleigh-like scattering, where tiny grains toss short wavelength light more than red. Chunkier grains give broader, greyer coats, muting everything evenly. The size, altitude, and patchiness of clouds matter. Patchy clouds can make measurements vary slightly from one transit to the next, as different parts of the limb take their turn under the lamp. Subtle shifts in depth and colour with time can betray changing weather. Winds choreograph heat and trace gases. Most hot, tidally locked planets, those with one side always facing their sun, face a harsh lamp on one cheek and eternal darkness on the other. Air warms, rises and races eastward, a pattern called superrotation, ferrying heat from day to night. When we map brightness across a rotation, the hottest spot often sits east of the substellar point. That hotspot offset is a wind signature. On cooler giants, clouds may pile up at the morning or evening limbs, painting different hues around the rim. Speculative. Some warm Neptunes may host shifting belts like Jupiter's, with stormy plumes that grow and fade over months. The ingredients of clouds follow simple kitchen rules. If the air cools below a substance's condensation point at a given pressure, grains form. Silicate clouds can loft on very hot worlds. Manganese sulfide may snow on cooler ones, though snow here means metallic flakes settling like glitter. Photochemical hazes sparked by ultraviolet light can bloom even where it's too warm for clouds, turning the sky into a reddish, tarry filter. On Titan, Saturn's moon, sunlight builds organic haze that drapes the world in butterscotch. We suspect distant planets do similar tricks with methane and nitrogen families. Weather paints the whole theatre, not just the limbs. On the day side, where we glimpse thermal glow during an eclipse, clouds can brighten a world by reflecting starlight or dim it by capping deeper, hotter layers. A high, reflective deck makes a planet look pale, but it also hides hot air beneath, lowering the infrared shine. Measuring both reflection and heat helps break ambiguities. Phase curves, brightness changes through a full orbit. Let us follow the moving patchwork, tracking when bright clouds rotate into view and when warm patches cool under night. Combining phase curves at multiple colours tells us which layers are cloudy and which are clear. How do we separate haze from chemistry? We lean on multiple wavelengths and on the shapes of spectral shoulders. Water vapour has broad features. If those are flattened but sodium is still visible, the veil is likely high and thin. If everything is smudged, the veil is thicker or made of particles tuned to those wavelengths. Retrieval methods include cloud parameters, like particle size and altitude, so the FITs can see when a dull spectrum prefers hazy answers. Yet degeneracies linger. A heavier atmosphere with small-scale height can resemble a lighter one with thick haze. We bring in mass and radius to estimate gravity, narrowing the wardrobe. Time adds a playful twist. Repeating observations can catch real weather. A transit that's a shade deeper one night might hint at more limb cloud, not just instrument drift, especially if colours shift too. Secondary eclipses that vary could point to dayside storms wax and wane. Speculative. We may catch lightning on ultra-hot giants as silicate clouds rub and charge, producing radio crackles that future arrays could hear. We've seen such sparks in brown dwarfs, star-adjacent cousins to giant planets. Exoplanet storms may not be far behind. To make sense of all this, we keep the theatre metaphor close. The star is the lamp, the planet, the actor, the atmosphere, the wardrobe, the winds, the choreography, and the clouds, the masks. Instruments are our ticket takers and ushers, guiding light to the right seats in the spectrum. Sometimes a costume hides the performer's face, sometimes it catches the light just so, revealing a glittered trim. By noting when the sequins flash and when the cape swallows the glow, we infer cut, cloth, and motion. The marvel is not just that weather happens elsewhere, but that, at such staggering distances, we can feel the draft when the door on a faraway stage swings open and a gust of alien air slips through. Now and then, the stage is too bright for us to see the actors at all. The lamp floods everything, and we squint into glare. Directly imaging a planet means building a visor for that lamp, and then focusing on faint faces in the wings. The tools are chronographs and starshades, clever masks and offstage screens that hush the star's spill so the planet's glow can rise above the hiss. A chronograph sits inside the telescope, using shaped stops and mirrors to cancel the star's diffraction pattern, the optical ripples that scatter light like waves around a rock. A starshade flies separately, a giant petal disk that blocks starlight before it even enters the telescope, casting a crisp shadow so we can peer close without dazzlement. The challenge is contrast and separation. Planets are dim compared to their suns, often a billion times fainter at visible light, and they stand right next to the blaze. We speak of the inner working angle, the smallest star-planet separation where the mass still works, measured in tiny arc seconds. Young, hot, wide-orbit giants are easiest. They glow with leftover heat from formation and sit far enough out for the mass to thread them. This is why the first directly imaged systems like the graceful quartet around HR 8799 are adolescent behemoths tens of times farther from their star than Earth is from the Sun. Adaptive optics on big ground telescopes sharpen the view by flexing mirrors hundreds of times a second, ironing out the wiggle of Earth's air. These systems create artificial guide stars with lasers, then adjust over and over to keep the point spread tight. Still, starlight leaks persist as speckles, stubborn faux planets that twinkle in and out. To sift real worlds from speckles, we use differential tricks. Angular differential imaging watches the sky rotate, while speckles from the instrument stay fixed. Spectral differential imaging looks at colour dependence, since speckles change differently with wavelength than a planet's light. Polarimetric imaging hunts for polarised reflection, a fingerprint of scattered light from a planet or disk. Once we see a point, we want to know what it is. A cool planet's brightness at different colours tells us its temperature, cloudiness, and chemistry. Methane absorbs near 1 and 2 microns. Its presence or absence can sort objects by class. Redder colours can indicate dusty, hazy photospheres, perhaps thick silicate clouds like those found in brown dwarfs. Over years, we can track motion to confirm the object is bound to the star, not a background imposter. Orbits gradually unfurl, offering mass clues when paired with models. Future missions aim to pull fainter actors from the wings. Space telescopes with exquisitely stable optics can hold a coronagraph steady enough to suppress starlight by factors of 10 billion. Designs like Habex and Louvois proposed pairing these with a starshade, whose petaled edge softens diffraction so the shadow is kind and dark. With that, we could image planets like Earth around nearby suns, separate their blue-white dots from the blaze, and even take spectra of their reflected light. From those, we could search for oxygen, water vapour, and other markers in context. The dream is an ensemble cast. Rocky worlds near the warm zone, cold giants nesting farther out, all seen in one frame. Even before such missions fly, giant ground observatories, the extremely large telescope, the Giant Magellan Telescope, the 30-metre telescope, will push into closer separations in the infrared. Their vast mirrors gather more photons and resolve finer angles, while improved coronagraph designs and wavefront control nibble away at speckles. High-dispersion coronagraphy combines starlight suppression with ultrafine spectroscopy, using the planet's own Doppler-shifted lines as a telltale to fish out its signal from the speckle sea. It's like listening for a specific singer in a chorus by tuning to their exact pitch and vibrato. Speculative. Some directly imaged worlds may show seasonal shifts as cloud belts wax and wane, or as storms rise and settle, changing colours subtly over years. We might even catch exomoons tugging their hosts, jittering the point's position like a dancer's partner guiding a step. For now, the images we hold feel like family portraits. Soft, precious, and humbling. Each speck is a place with weather, dawns, and nights, orbiting under a sun that looks like a star to us. The stage is vast, the lamp unblinking, but the visor works. When the glare eases and the face appears, we recognise the simple truth. We're not just watching light, we're meeting neighbours. Imagine sniffing the theatre air and guessing whether the audience just applauded a comedy or a tragedy. The scent is a clue, but context matters. Spilled wine, old velvet, and perfume can mislead. When we talk about possible signs of life on distant worlds, we're doing a similar thing with light. We look for sets of gases and surface hints that don't sit comfortably with chemistry alone. A classic pair is oxygen and methane. Oxygen is reactive. Leave it to itself and rocks. Microbes and volcanoes mop it up. Methane burns in oxygen-rich air. Together, in steady amounts, they suggest a continuous source. On Earth, that source is biology, but planets are varied stages. An atmosphere's composition rests on geology, sunlight, water, and the star's mood. Oxygen without life can build up if water is broken apart by ultraviolet light and the hydrogen escapes, leaving oxygen behind. On small hot worlds close to feisty stars, this false positive is a real possibility. Methane can bubble up from rocks, made deep underground and released through vents. Another sometimes mentioned gas is phosphine, which on Earth is associated with microbes in oxygen-poor niches, but it can also arise in violent reducing environments. Any single marker can be misleading. It's the ensemble and the backdrop that matter, so we aim for context-rich biosignatures, combinations of gases, surface reflection patterns, and temperature-light relationships that can't be explained away by plain physics and chemistry. Water vapour alongside oxygen hints at a moist biosphere rather than a desiccated husk. A modest level of methane, persistent under bright stars, points to continuous replenishment. The presence of nitrous oxide, a product of life on Earth, would be intriguing in company. A red edge in reflected light, a sharp rise in reflectance at the colours used by chlorophyll, could signal vegetation-like pigments, though alien biochemistry might choose different paints. Speculative. Some worlds may host pigments suited to red dwarfs, using deep crimson light, shifting the edge. Stellar type is crucial. Cool red dwarfs bathe planets in ultraviolet patterns different from our Sun, influencing ozone layers and breaking molecules at different rates. Planets close to them may be locked with one face staring forever at the lamp, altering climate and circulation. Flare activity can strip atmospheres or fill them with photochemical haze, masking or mimicking signals. We must measure the star's spectrum and variability, then model how its light pumps the planet's chemistry. Surface gravity and temperature shape whether gases linger or leak. A light, heated atmosphere can bleed into space, taking precious hints with it. Observationally, we'll rely on a mix of techniques. Transmission spectroscopy during transits can sniff the limb, good for water vapour, methane, and other molecules if clouds don't smother them. Secondary eclipse and phase curves can isolate day and night contributions, hinting at heat transport and cloud cover. Direct imaging, when it reaches Earth-sized worlds, will let us read reflected light spectra across seasons, searching for covarying signals. Polarimetry, the measurement of light's preferred direction, can reveal oceans through a glint and help separate clouds from surface. Each adds a thread. Together they form a tapestry strong enough to tug. We should be wary of our own eagerness. The line between signal and artifact is thin. Instrument quirks can cast shadows that look like features. Stellar spots can imitate molecules in noisy spectra. Retrieval models can be biased by the assumptions we bake in, like what types of clouds we allow or what chemical pathways we include. The best guard is humility, replication, and independent methods converging. When signs hold across instruments, across colours, and across epochs, confidence grows. There's also a wider view, technosignatures. These are hints of technology, like narrow radio lines or unusual infrared waste heat. They sit outside the main script of planetary atmospheres, but they remind us that life's footprint could be broader than breath alone. Speculative. If we ever saw a peculiar, seasonless, uniform spectral edge coupled with artificial-looking glints, we'd have questions. Ultimately, the careful talk around life's signs recognizes that planets are complex stages, with many ways to put on a show. We're learning the backstage, how rocks, seas and skies exchange gases, how sunlight paints chemistry, how volcanoes, lightning and impacts stir the pot. Only with that foundation can we notice when the script goes off kilter in a way that screams biology. Even then, we'll ask for encores and for new acts to confirm the theme. The joy is not in declaring victory, but in building a case that respects nature's creativity. If life has written its lines elsewhere, it will likely speak in dialect. Our task is to listen well, ask fair questions, and let the evidence lead. Picture a troupe travelling from town to town, sometimes setting up in grand halls, sometimes in small community centres. Exoplanet systems are like that range of venues, each with its quirks shaping the performance. As we catalogue worlds, we're building a map of how planets form, move, and evolve, and what that says about our home stage. The surprises sharpen our sense of what is normal and what is rare. Our solar system has no super-Earths, those in-between actors heavier than Earth but lighter than Neptune, yet they're common elsewhere. Hot Jupiters, enormous gas giants hugging their stars, are rare overall but hard to miss, and they forced us to rewrite the opening scenes. From the timing of transits, the sway of stars and the colours of atmospheres, we infer how systems were assembled. Migration seems common, Giant planets likely formed far out in cool, dusty nurseries and then slid inward through the protoplanetary disk, shepherded by drag and resonant kicks. Some were flung onto eccentric paths by gravitational tussles with siblings. These motions shape the inner architecture, carving gaps, piling up super-Earths, or scattering them. The resonant chains seen in some systems, planets orbiting in tidy numerical rhythms, hint at gentle migration and damping. Where chains are broken, we see the aftermath of scuffles. Atmospheric metallicity tells us about the ingredients and timing of growth. In our system, smaller giants like Neptune are more metal-rich than Jupiter, suggesting they gobbled more solids relative to gas. We see similar trends beyond, with some hot Jupiters showing inflated metallicities, perhaps owing to late accretion or skyscraping balloons of heat. The distribution of densities among small planets reveals two families, rocky super-Earths and puffy mini-Neptunes with thick envelopes. Photoevaporation, the stripping of light gases by high-energy light, can sculpt this divide, carving out a valley in sizes. Planets closer to their stars lose their gas coats, leaving compact rocky cores, while those a bit farther keep their airy capes. Climate lessons flow back to us. Phase curves teach us how heat moves without oceans or continents, when winds alone shoulder the load. Some planets shun energy efficiently, cooling their day sides. Others hoard heat, glowing like braziers into the dark. Clouds appear where circulation favours them, at the evening limb on some hot giants, perhaps as condensates form in cooling air. These patterns test our climate models, the same equations we use to forecast weather at home, stripped to raw essentials. If our models fail on alien stages, we know where our understanding needs mending. The diversity of worlds also widens our sense of habitability. The habitable zone is a simple sketch, where liquid water could persist on a rocky surface, but greenhouse gases, cloud feedbacks, and planetary rotation morph that sketch. A tidally locked planet around a red dwarf might keep a snug eye-shaped ocean under its dayside cloud umbrella. A world with thick haze could cool itself despite extra sunlight, while a world with few clouds might overheat. The presence of a giant neighbour can stabilise or stir climate, nudging a planet's tilt and seasons. Water delivery matters too. Icy bodies from the outer disk may have ferried ours. Similar deliveries elsewhere might be routine or not. We also learn about longevity. Systems with tightly packed inner planets test the limit of stability. Transit timing variations reveal whether tugs are gentle or dangerous, hinting at long-term harmony. Astrometry promises to weigh wide companions that can tilt inner stages, inducing misaligned orbits we then see in stellar wobble signatures. Pulsar planets remind us that life's stage can be rebuilt in wreckage, although such harsh lamps are unlikely cradles. Speculative, across billions of years, many systems may pass through multiple acts, with planets migrating, losing air, and perhaps gaining new coats through outgassing, reshaping prospects along the way. Even small, quiet details echo home. Clouds made of unfamiliar stuff still follow the same physics of condensation. Winds adjust to pressure gradients just as Earth's do. Chemistry dances along pathways set by bond energies and sunlight's push. This kinship binds our models and their targets. When we tweak a model to fit a hot Jupiter's strut, we may sharpen forecasts for tropical cyclones or winter jets on Earth, because the core dynamics rhyme. Likewise, studying atmospheric escape under fiercer radiation helps us understand how young Earth held onto its air, and how Mars lost much of its own. In that sense, distant stages teach us how to read our own theatre more honestly. We're one company among many, our set one of countless arrangements. Seeing the range, tight quartets of super-Earths, loose pairs of giants, lonely wanderers, keeps our pride in check and our curiosity awake. The plots are shared, birth in a disk, growth by gathering, tempering by light and shadow, change through encounters. The surprise is not that we differ, but that we recognise ourselves in so many refrains. Hold a magnifying glass over a bright poster, and the letters swell. Now imagine the glass is gravity itself. When a star passes in front of another from our viewpoint, its gravity bends and focuses the background starlight, briefly brightening the distant source. This is microlensing, a natural lensing effect predicted by relativity. If the foreground star hosts a planet, the planet's gravity adds a smaller lens, a quick flicker riding on the main brightening. We never see the foreground system directly. We only watch the background star's light curve, a rise and fall over days or weeks, with a telltale blip when the planet's lens crosses our line of sight. This method is a gift for finding worlds that other techniques miss. It's most sensitive to planets at a few astronomical units from their stars, where icy giants and cool super-Earths live. It can even spot free-floating planets, actors between theatres, not bound to any lamp, revealed when their own gravity briefly boosts a background star. The signal's shape depends on alignment geometry and speed. A perfect alignment would produce an Einstein ring, a circle of light, but in practice we see asymmetric brightening. The planet's signature is a short deviation whose timing gives us the planet's separation in units of the Einstein radius, while its size hints at the planet-to-star mass ratio. Surveys like OGLE and MOA scan dense star fields, especially toward the galactic bulge where background stars abound. They flag ongoing events that follow-up teams then monitor rapidly. The events are once only, the alignment doesn't repeat. That's both a blessing and a curse. We get snapshots of planets far from their suns and a census of cold worlds, but we can't go back and check at leisure. To estimate actual masses and distances, we rely on extras, parallax effects as Earth moves, or subtle changes from the finite size of the source star. Sometimes high-resolution images years later can separate the lens star from the background, pinning down properties. One charm of microlensing is its democracy. It doesn't care whether the host star is bright or faint, as long as it's in the right place at the right moment. That opens a window on low-mass stars and faint hosts where other methods struggle. It also reaches to low-mass planets. Deviations from Earth-mass worlds can be strong enough to spot, given good coverage. Speculative. Future space-based surveys might net Mars-mass planets, rounding out the census of rocky building blocks across the galaxy. Space missions can transform the field. Observing from orbit offers steady views, and, if paired with ground observations, a clean parallax as the two vantage points see slightly different curves. The Nancy Grace Roman Space Telescope plans a microlensing survey toward the bulge, with the cadence and stability to find thousands of events and hundreds of planets. Its sharp eyes will help resolve lenses from sources later, turning more mass ratios into actual masses. Combining Roman with ground arrays would catch short deviations that might otherwise slip between observations. Yet microlensing has limits. Because events don't repeat, we usually can't get spectra or phase curves. Habitability is hard to gauge, and atmospheres remain out of reach. The method also favours crowded fields where blending, light from unrelated stars in the same pixel, can bias measurements. Careful modelling helps, but uncertainties linger. Still, as part of the ensemble, microlensing fills a vital role. It tells us how common cold planets are, how often small worlds share orbits with giants, and whether planetary systems like ours, with multiple zones, are ordinary or not. Think of it as catching a travelling show that passes through town without warning. We gather quickly, we watch attentively, and we learn what we can from that brief brightness on the wall. The actors remain silhouettes, but their presence and spacing become clear. Over many such shows, patterns emerge. Certain roles recur, others surprise. Some acts are crowded, others sparse. In that accumulation, the galaxy's planetary story comes into focus, with cold scenes given their due alongside the hot, bright ones that earlier methods favour. If the star is a spotlight, astrometry is watching the person holding it sway as unseen dancers tug at their sleeve. A planet and its star orbit a shared centre of mass. From afar, the star doesn't sit still. It traces a tiny ellipse on the sky. Astrometry is the craft of measuring that motion with exquisite precision, down to millionths of a degree. The size of the wobble depends on the planet's mass and distance from the star, and on how far away the system sits from us. Big planets far from their suns induce big loops. Small worlds close in, make almost imperceptible squiggles. This method complements the stellar wobble measured along our line of sight, known as radial velocity. Radial velocity tells us about back and forth motion from Doppler shifts in spectra. It gives a minimum mass because we don't always know the tilt of the orbit. Astrometry adds the side-to-side motion on the sky, delivering the missing inclination, and therefore the true mass. Together they sketch full orbits in 3 dimensions. For long-period planets, astrometry shines where radial velocity struggles because the cycles are slow. A decade of precise positions can reveal giants as far out as Jupiter and beyond around nearby stars. The European Space Agency's Gaia mission is the current master of this art. It scans the sky over and over, measuring star positions, motions, and subtle accelerations. As its catalogue matures, it will uncover thousands of big planets through their host stars' meandering paths. Some detections come as hints, accelerations that imply something is tugging, even if the full loop isn't complete. Follow-up with radial velocity can confirm and refine those suspects. For the closest, brightest systems, we may even see the planet directly and tie all three strands together: imaging for separation, radial velocity for speed, and astrometry for tilt. Astrometry is fussy. It must correct for parallax, the apparent yearly shift of a star as Earth orbits, and for the star's own straight-line proper motion across the sky. It must also face down instrumental drifts and calibrations. Tiny optical distortions can masquerade as wobbles, but steady calibration, redundant scanning, and clever modelling tame much of this. In the end, the residuals, the little leftover wiggles, carry the planetary signal. What can we learn beyond mass and orbit? Quite a bit. The orientation of the orbit in space, including whether the planet's path aligns with the star's equator, hints at how the system formed and evolved. Misaligned or retrograde planets, those going the wrong way, point to violent pasts with tilts from close encounters or torques from companions. Astrometry across multiple planets in one system can catch resonances and joint dances where mutual tugs tweak each loop. Over long baselines, it can even flag distant companions we can seek with direct imaging. Astrometry also reaches to stars that are poor transit hosts. Bright, nearby suns seldom line up for transits, and some have busy surfaces that muddle radial velocity at small amplitudes. A positional nudge sidesteps those issues, though activity can still jitter the photocenter if star spots shift the apparent center of light. Models of stellar surfaces and time averaging help separate true motion from such illusions. Speculative. As instruments improve, micro-arc-second precision from the ground might become routine for the very brightest stars, opening a path to weighing super-Earths at habitable distances around our nearest neighbours. In the theatre metaphor, astrometry is the quiet observation of the stage crew, the subtle cues that betray a hidden duet. We don't see the partner directly, but the lead steps tell us they're guided. When combined with other methods, the portrait sharpens. A planet measured by astrometry and radial velocity has a secure mass. Add a transit and we gain radius and density. Add spectra and the air speaks. Each method alone offers a partial view. Together they whisper a full scene into focus. The beauty of astrometry is its reach outward, to wider orbits and longer tails, extending our grasp beyond the immediate footlights. Listen to a drumline that should hit on the beat, then notice the taps arriving a shade early or late. Something off stage is tugging the tempo. That's the essence of transit timing variations. When multiple planets circle the same star, their gravity pulls on one another. Those tugs speed up or slow down each planet slightly, so the moments when they cross the star, the transits, drift from strict periodicity. By measuring those drifts, we can weigh the planets, probe their orbits, and even find worlds that don't transit at all. If two planets lie near a resonance where their orbital periods are in a simple ratio like 2:1, the tugs stack neatly, and timing variations grow strong. The pattern of early and late arrivals repeats over a longer super period, the time it takes for the near commensurate orbits to realign. The amplitude of the variations depends on masses and how close to resonance they sit. The shape depends on eccentricities and mutual inclinations. In some systems, the timing swings reach minutes. In others, they are subtle but accumulative, revealing themselves after many transits. Transit duration variations add a second strand. If the path across the star shifts because of nodding or precession, the transit takes a little longer or shorter. That can hint at tilt changes or additional companions. Combining timing and duration changes with transit shapes gives a rich picture of the geometry. For densely packed systems, TTVS offer one of the few ways to weigh small planets. Kepler's harvest includes pairs and trios where masses come almost entirely from these rhythmic wobbles. Kepler 36 is a classic. Two planets with similar orbits but starkly different densities, exposed by their mutual tugs. Modelling TTVS is a delicate dance. It means integrating the orbits forward under gravity and adjusting masses and shapes until the predicted timings match the measurements. Degeneracies appear here too. Certain combinations of mass and eccentricity can produce similar timing patterns. Near first-order resonances, where the effects are largest, these degeneracies can be stubborn. Breaking them may require independent hints from radial velocity or, for bright stars, transit spectroscopy that confirms which planet holds a thicker atmosphere. With enough transits, though, the patterns often give way, and we prise open not just masses but hints of past migration, because resonant chains are fossil records of disk-era moves. TTVs can also flag hidden actors. A non-transiting planet tugging a transiting one will shift its schedule, leaving a phasing and amplitude that betray the unseen companion's mass and orbit. This is a way to discover inclined or outer planets that otherwise slip by. In some cases, the additional planet might be distant and massive, tilting the inner trio and hinting at a complex history. Speculative. In compact systems around red dwarfs, TTVS might reveal exomoons, tiny tugs layered on top of planetary rhythms, though distinguishing moons from planets is hard. Stellar activity can complicate the read. Star spots, when crossed by a transiting planet, can mimic timing shifts if we mismeasure the transit center. Careful modelling of transit light curves and using multiple wavelengths to spot crossings can reduce the confusion. Stable, space-based photometry helps. Kepler and TESS provide dense series where patterns emerge cleanly. Ground-based follow-up can extend baselines, catching variations over years. In our theatre, TTVs are the partner's unseen hand on the dancer's shoulder, altering the entrance by a half step. They're proof that systems are not sets of isolated orbits, but ensembles reacting to one another. These tugs speak of pasts spent in disks and of present-day balances on the edge of resonances. As we collect more such rhythms, we'll refine our census of small planet masses, especially where radial velocity falters. And by mapping where resonances hold or break, we'll read the friction and froth of the birth stage, where gas and dust still muffled the score. On a dark headland, a lighthouse sweeps a steady beam, and if you time the flashes, you can set your watch. Some neutron stars, the collapsed cores of massive stars, are such lighthouses. They spin and send radio pulses at ferocious regularity. Tiny changes in the timing of those pulses can reveal planets tugging the neutron star, shifting it as they orbit together. In the early 1990s, this is how the first confirmed exoplanets were found, crowded around a pulsar named PSR B1257+12. The discovery was astonishing. Planets in the harshest theatre, circling a lamp born from a supernova's wreckage. Pulsar timing works because the clock is so precise. Any planet induces a wobble in the pulsar's motion around the system's centre of mass. As the pulsar moves toward or away from us, the path that the radio waves travel lengthens or shortens by small amounts, altering arrival times by microseconds or less. The pattern of these timing residuals maps the planet's orbit. Multiple planets produce overlapping signatures, which can be untangled with careful modelling. The method is exquisitely sensitive, reaching masses much smaller than Earth in tight orbits, and Earth mass at greater distances. The environments around pulsars are extreme. Radiation and particle winds are intense. If planets survive the supernova, they're hardy. The two leading ideas for their origin are survival. Planets that formed around the star before it exploded and somehow remained bound, or rebirth, where a debris disk from the explosion or later accretion grows new planets. The composition of such worlds may be exotic, perhaps rich in heavy elements or with unusual atmospheres. Speculative, some could be stripped cores, metallic and dense, with thin exospheres glowing under bombardment. Pulsar timing arrays, networks of pulsars observed regularly, are used to hunt for gravitational waves from supermassive black hole binaries by measuring correlated timing drifts across the sky. In the process, they refine techniques that also feed back into planet searches. The stability and calibration needed to catch nanosecond shifts push the limits of instrument control and data analysis. While pulsar planets are rare compared to planets around normal stars, the method showcases what precision can do when nature provides a clock. We shouldn't expect many comfortable worlds in these theatres. The light is wrong, the wind is fierce, and the neighbourhood is noisy. But the existence of any planets here teaches resilience and breadth. Planet formation, like a touring troupe, finds ways to set up even in bombed-out halls. The timing technique itself has inspired ideas about using other regular cosmic clocks to detect tugs, and it underscores a broader truth. Variety in methods uncovers variety in worlds. Pulsar planets also invite creative follow-up. If any transit, the eclipse of the pulsar's beam would be sharp, but the odds are slim given tiny star sizes and random alignments. Direct imaging is out of reach. These stars are too faint in visible light. Radial velocity is meaningless without spectral lines, so the timing stands alone, authoritative in its domain. The planets we know here include a pair in resonant orbits, echoing patterns seen around sun-like stars, a reminder that gravity composes similar harmonies even under different lamps. In the theatre of the cosmos, pulsar timing is the art of listening to the metronome and hearing a footfall out of place. It proves that planets are not picky. They turn up amid ashes, they circle embers, they test our definitions. Each method broadens the canvas. Each new stage challenges us to adapt our eyes and ears. With pulsars, we learn to value the silence between beats as much as the light that fills a hall. Imagine watching an actor circle a stage under a hot lamp. When they face us, their face gleams. When they turn, we see the cooler back. Planets do the same. As they orbit, we see changing brightness from reflected starlight and thermal glow, painting a phase curve across one full circle. If the planet slips behind the star, we momentarily lose its warmth and shine. That brief drop is a secondary eclipse. Together, phase curves and eclipses let us map heat, reflectivity, and in some cases winds and weather on worlds we cannot resolve. Reflected light depends on albedo, the fraction of light a planet bounces back. Smooth clouds boost it. Dark, absorbing surfaces lower it. Thermal emission tells us how hot the day side is, and how well the planet moves heat to the night side. A high day-night contrast implies poor redistribution, perhaps because winds are sluggish, or the air is thin. A small contrast suggests swift jets ferry warmth around. By measuring brightness at multiple colours through an orbit, we can build a crude weather map. This patch brightens in the infrared, that arc shines invisible, clouds likely pile up here. On hot Jupiters, secondary eclipses have given us day-side spectra, showing water vapour, carbon monoxide, and the shape of the temperature profile. Some show temperature inversions, hotter layers above cooler ones, likely due to absorbing chemicals like titanium oxide, or to strong stellar irradiation redistributing heat. Others lack inversions, suggesting different chemistry or absorber loss. Phase curves often show the brightness peak shifted eastward from the substellar point, the hotspot carried by winds. The amount of offset depends on rotation rate, drag from magnetic fields, and radiative timescales, how quickly air gains and loses heat. Clouds influence these curves. Bright, reflective clouds can offset the visible light peak toward the morning side, where clouds condense as air cools from the night side passage. Infrared peaks may still lean east if winds dominate. On cooler Neptunes, high-altitude hazes can dim features and complicate the read, while on ultra-hot giants, daysides may be too hot for most clouds, leaving a stark thermal signal. Speculative. Some metal-rich worlds might sprout reflective clouds of exotic salts on the night side that evaporate at dawn, shifting the phase curve with a daily rhythm. Eclipse mapping is a neat refinement. As the star covers and uncovers the planet, the shape of the light curve's edges, ingress and egress, encodes how brightness is distributed across the day side. With careful modelling, we can reconstruct coarse maps, finding bright spots or banded structures. This is limited by signal strength and cadence, but with Webb and future instruments, sharper maps beckon. Combining eclipse maps at different colours yields a layered view, high clouds in one band, deep hot layers in another. For smaller, temperate planets, phase curves are faint, but not impossible. Reflected light curves can measure albedo and hint at oceans if a specular glint appears, a mirror-like flash at certain angles. Polarized light can emphasize such glints. Thermal phase curves probe climate. A modest day-night contrast might imply a thick atmosphere. A strong one could suggest thin air or bare rock. Teeming phase curves with transit transmission spectra knits a more complete climate sketch, checking whether the limb resembles the day side and whether clouds cluster where expected. Physics terms here are simple. Albedo is reflectivity, emission is heat glow, hotspot offset is the shift of the brightest point from the spot directly under the star. Heat redistribution efficiency is how well winds and circulation spread warmth. Radiative timescale is how fast air responds to heating or cooling. These are levers. By adjusting them in models until phase curves fit, we learn about drag, chemistry, and energy budgets. We also gauge energy balance, how much of the star's input is reflected versus re-radiated, and whether internal heat matters. We must mine the star's contribution. Stellar variability can masquerade as planetary phase signals, especially for active stars. Observing multiple orbits and using control wavelengths help isolate the planet. Instrument systematics can imprint false curves. Decorrelation and independent analyses keep us honest. When curves persist and match across instruments, confidence climbs. In the theatre frame, phase curves are the actor's turning face, and secondary eclipses are a brief step into the wings. They let us feel the heat on one cheek and the cool on the other, hear the rush of wind in unseen corridors. Some worlds run hot and bright, with jet streams hauling their hotspots. Others wear pale veils that glimmer before dawn. As we watch more orbits, the patterns cohere into climate classes, prototypes that sharpen our sense of possibility. If you'd like more quiet explorations like this, consider subscribing. And if you have a moment, share where you're listening from and the time. We've walked together from scarves of air to clouds and masks, from star visors to careful breaths, from lensed posters to swaying lamps, tapping rhythms, cosmic metronomes, and the turning faces of distant actors. Thank you for keeping me company in the dark of the hall. We'll keep looking out, steady and curious as the cast grows and the scripts deepen. What small detail in this cosmic theatre would you like us to linger on next?